Bam, Mr. True. In this video, we are going to introduce mathematical induction proofs and work through 3 examples to help you get through your homework. Now, at any level of mathematics, when you're just learning them, proofs are difficult. So, I'm going to break this up into probably more steps than your textbook does to hopefully make it easier to understand the process you need to walk through and understand what you're doing when you're all done. And within these multiple steps, 6 steps, we're going to contain the 3 key concepts of an induction proof that your textbook is pointing out. The first step is show that S of 1 is true. Now in my pre-calculus class, this lesson follows the introduction or review actually of arithmetic and geometric sequences that you learned in Algebra 2, or that my students had learned. The reason why, one of the reasons why, is to reacquaint ourselves with subscript notation. So when I say that you're going to prove or show, not prove, that S of 1 is true, S of 1, when you say S of 1, that subscript of 1 means that N is equal to 1, or whatever the subscript letter your textbook is using, K, I, whatever. And, well, you'll see this in the example, but you're going to show that it works for the first term in this equation that you have, if you're given a sequence or an equation. We're going to assume S of k is true. S of k is going to be the original statement, and in our first 2 examples, or actually all of our examples, excuse me, it's going to be a sequence of additions. Basically maybe an arithmetic or geometric sequence, but just a sequence of additions. And that equation we're going to assume to be true. We did, after all, just check that it worked for at least the first term. Force substitute in k plus 1 everywhere there's a k. So this is going to set up a S of 1 equation. The right side of this equation will need to be what you get in the last line of your proof. You want to make that match. This particular step is kind of like me adding an extra step into what you might see in a textbook, depending on how it's written, of course, to just help clarify, where are you going with this proof. We're going to assume the given an equation or statement is true, and then we're going to substitute in everywhere there's a k plus 1. And that's not really the proof or part of the proof, but it is going to show you what the last line of your proof should be, so you know what goal you're working towards. This will be a good step that you want to do for those induction proofs where you have, like my 3 examples, a sequence of additions that and it's a 2-sided equation. Start the next part of your proof by rewriting the S of k equation, the original equation given, and then we're going to take or find the S of k plus 1 term and add that S sub k plus 1 term to both sides of the equation. Again, my 3 induction proof examples are going to be on the left side, a series of, or a sequence of additions of terms. And that list is going to have an unknown or undetermined length. So our last term is going to be our S sub k term, and we're going to extend that general sequence by 1 more term and add that term to both sides of the equation. Then the rest of the proof is going to be, we're going to simplify the right side of that equation and see if we can't, with some algebraic steps, get the right side of that proof, the right side of that equation, to equal what you got in step 3, where I'd like to say you forced in the k plus 1 substitution, where in step 3 you found out what should that right side of the equation be when we're done with our induction proof. And if you can get the algebra to make the right side of your proof look like the right side of the equation you got in this step 3, you're done with the proof. And again, these steps are for when you are given a sequence of additions on the left-hand side of, let's just call it an identity or your equation, and then and then sort of like a summary expression on the right-hand side. It's kind of like think of the partial sum formula for the arithmetic sequences. Only we're going to be given specific types of sequences where you can expect to see what comes up. So let's look at those 3 examples. Here's our first example. We're going to prove that 6 plus 12 plus 18 plus 24 plus ... because this sequence of additions does not have to have a set number of terms in it, plus 6n is equal to 3n times n plus 1. This happens to be an arithmetic sequence because we're constantly adding by 6. So let's get started. This, by the way, is our S sub 1 term in the sequence, and this last general term is our S sub n term. Okay, so is this true regardless of how many terms that we have in our sequence? Well, step 1 is to prove that it is true for at least the first term. So, S sub 1, well, S sub 1, step number 1, that's what I was trying to remember. S sub 1 is 6, and if we're looking at the first term in the sequence, 6, if we're looking at the first term, our subscript or our n is 1. So we're going to take the value of 1 and plug it into the right-hand side. So 3 times 1 times 1 plus 1, well, 3 times 1 is 3, 1 plus 1 is 2, and yes indeed, 3 times 2 is equal to 6. So we have shown that it works for the first term, that S sub 1 is true. The second key component of an induction proof, since this equation worked for one term in the sequence, we're just going to assume that it's true. So we're going to assume that S sub k is true. We're going to take the n out and replace it with k. It's kind of a formality for proofs. Kind of just think you're not allowed to use a word in the definition of that word. So we're going to take the n out and replace it with k just as a formality for the proof. We're trying to prove this, so we can't actually use that in our proof. So we're going to assume that this is true, but we're going to take the n out and replace it with k. And now, just for extra clarity, I'm going to force in, my third step I said was going to be to force in a substitution of k plus 1 to help me find out what should the right-hand side of my proof be when I'm done with it. So this is an extra clarity step. It's not really part of the proof. We're going to find our S sub k plus 1 statement. So I'm going to go through here. Everywhere there's a, whoops, I do that all the time. I go to write my S sub k and I keep putting the n's back in it. So everywhere there's a k, I'm going to plug in k plus 1. Make a note on the right-hand side. Every time I did that substitution, and every time I do a substitution, I put a set of parentheses where the variable used to be before I do my substitution. That's going to help make sure I don't make any sign errors, and it's also going to make sure that I don't forget, I don't get confused with what I'm substituting in with what's already in the equation. This last parentheses has a k plus 1, and I'm plugging in k plus 1. So sometimes students will forget to write k plus 1 for what I'm plugging in, and then the additional one that was already in the equation. This comes out to be 3 times k plus 1. And then, of course, 1 plus 1 is equal to 2. These parentheses are here just to show the substitution, but there's no leading coefficient, there's no exponent, and there's no division below that parentheses. And there's nothing I can do algebraically inside of it. So it was just there as a placeholder for me to do that substitution, and I can go ahead and just do the 1 plus 1 is equal to 2. This had better be the last line of the rest of my induction proof. When I get back to actually doing the proof, that needs to be my last line. Step 4, again, just for clarity's teaching, I'm going to rewrite the S sub k statement. Okay, I'm leaving some extra space because I have limited room here, and I want to get to step 5, which is add the s sub k plus 1 term to both sides. This is the original left-hand side of my sequence, going from 6 to 6k. So this is my s sub k term. I want to extend that sequence by one more term. So I'm going to go to my last term, which is 6k. I'm going to take the k out, substitute in k plus 1, like I did up here in the previous step, but it's going to be different because I'm only going to substitute into my left-hand k, because I just want to take the sequence and extend it by one more term. And unlike this previous step where I just wanted to see what the end of the proof looks like, or should look like, I'm going to take this s sub k plus 1 term and add it to both sides of my proof, or my equation. And highlight it in yellow, hopefully you can see that, to really emphasize what I'm doing. Now I might run out of room, so I'm going to go ahead and erase these. So notations, just be aware that the difference between this step, my 5th step, and my 3rd step is I'm going to my last term on the left, which is my s sub k term. I'm extending that sequence by one more term and finding my s sub k plus 1 term and adding that to both sides. Okay, so now my last step is to work with this right-hand side and see if I can get the right-hand side of this, now what I'm finishing in my proof, see if I can get this to match the right-hand side of my s sub k plus 1 statement. So, now, you can do this however you like. I got a lot of algebra to do. Usually this part of these proofs, for these sequence type problems, really just involves maybe a little bit of Algebra 1 and Algebra 2 skills to finish the proof. So you might take the 3k and distribute it through these parentheses, take the 6 and distribute it through those parentheses, and then start adding like terms, and with this particular example end up with a trinomial, and then decide to factor it. Just to show you a little bit of a tip here, and to do it sort of a slicker way, I only have one plus sign in between these two terms. I have addition signs in here as well, but they're inside parentheses. I have two terms in the right side of this equation, and those two terms both have a common factor of k plus 1. So to speed things up a little bit, I'm going to take the common factor that's in each of these two terms, the k plus 1 factor, and divide it out, factor it out, kind of like 2x plus 10 equals 2 times x plus 5, where I divided 2 out of both of those terms. So I'm going to take this k plus 1 and pull it out of each of the terms. And what is left? 3k times k plus 1 divided by k plus 1 is going to leave you with 3k, and 6k plus 1 divided by k plus 1 is equal to 6. Okay, so I've done a little bit of simplification, but I still do not have my right side equaling what I had in my s of k plus 1 statement. Well, 3k and 6 both have a factor of 3. So I'm going to factor a 3 out of both of these terms, just like I just factored the k plus 1 out of those two terms, and I get this. 3k divided by 3 is equal to k. 6 divided by 3 is equal to 2. And you might be going, is it okay to just float that 3 way out front? Well, isn't 5 times 3 15 and 3 times 5 15? Yes. Multiplication is commutative. And hey, by the way, I just finished my first example. Bam! Second example. Now, this one involves some exponents, so somewhere near the end we're going to have a little slowdown, a little discussion about how you work those out. So we're going to prove that 2 plus 6 plus 2 times 3 to the first. This happens to be 2, or second, excuse me. This happens to be 2 times 3 to the first. So 2 plus 6 plus 2 times 3 to the second plus the pattern continues, dot, 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 until you get to your S of k term, which is 2 times 3 to the n minus 1. That sequence of additions equals 3 to the n minus 1. So step 1, show that it works for the first term. And there you go. Bang! 2 equals 2. Wow, rocket science. Step 2, assume that S of k is true. And that just means rewrite it, take the n's out and plug it in with k. And let me pause here for just a second. Okay, back to the problem. So we're assuming this to be true. Now in step 3, we're going to take the k out, plug in k plus 1, to see what the end of our proof should look like. So we have 2 plus 6 plus 2 times 3 squared plus 2, that should be a k again. Told you to do that all the time. Plus 2 times 3 to the k plus 1 minus 1 equals 3 to the k plus 1 minus 1. And this ends up being 1 minus 1 is equal to 0, so this numerator can just become 3 to the k. Now, in step 4, we're going to rewrite S of k, and let's see here, 2 plus 6 plus 2 times 3 squared plus okay, so I'm rewriting, to start the rest of my proof, I'm rewriting S of k, and again, we're going to add the S of k plus 1 term to both sides. So that means I'm going to take this term, I'm going to plug in k plus 1, which actually I just did up here, so I know it's going to be 2 times 3 to the k, and add that to both sides. And so I just did step 4 and step 5, and now we're going to simplify the right-hand side and see if we can't get this to show up again at the end of our proof. So we have 3 to the k minus 1 plus 2 times 3 to the k. So we have what appears to be 3 pretty simple little terms, but I've had some students really have some issues on how to add 3 to the k, or something similar to this, plus 2 times 3 to the k minus 1. A lot of students want to say that, well, if they're really struggling, they might just do 2 times 3 is 6 and mess up the order of operations. They might want to go 3 and 3 is 6. But you want to look at this as if maybe in algebra you were doing x squared plus x squared, where you have like bases and like exponents, just like we have here, like bases and like exponents. And we are adding like terms. These x squares have leading coefficients of 1. And so when you put these together, you just add the leading coefficients of 1 and 1 is 2, and you get 2x squared. So this is actually a little bit easier than the one I did in my class. I added a little bit to it to attempt to make it more complicated, but I'm giving you sort of a natural hint here that this is a base and an exponent and a base and an exponent. It looks a little funny because I know what the base is, but we still need to deal with like that leading coefficient. And this term is letting you see that 3 to the k has a leading coefficient of 2, or there's a multiplication of 2 out front, just like there's a multiplication of 1 in front of this first 3 to the k. So when I do 1 times 3 to the k plus 2 times 3 to the k, I'm going to add those numbers out front and get 1 plus 2 is equal to 3. And then we're going to just copy this down, 3 to the k minus 1. So now what do? Because this still doesn't exactly match 3 to the k plus 1 minus 1. Well, what do when you multiply like bases? This addition, I have the base on this exponent that I just basically copied down. 1 and 2 makes 3. The leading coefficients, if you will. It sounds funny to say that because I know what this base is as opposed to our normal algebraic thing where the base is a variable. Well, this 3 has an exponent of 1, right? When we don't write exponents, it's assumed to be 1. And when you multiply like bases, you add those exponents. So this is equal to 3 to the k plus 1 minus 1. And last time I checked, that was the end of my S sub k statement. So my proof, my second example, is done. Our third and last example is we're going to prove the summation of 2 over I times I plus 1, where the lower index is 1 and the upper index is n, is equal to 2n over n plus 1. Now this question looks quite a bit different than my previous two examples, but indeed it's actually really not. We're going to walk through the exact same process because the summation symbol is basically just shorthand notation for repeated addition. In my previous two examples it had exactly that. A sequence of additions on the left-hand side, and then it equals some kind of summary sort of shorthand expression we can use on the right. So let's get this started. Again, we're going to prove that S sub 1 works. So what about S sub 1? Well, in summation notation, to find the first term, you don't automatically plug in 1. It's not like the subscript notation because the lower limit does not necessarily have to start with the value of 1. It could be 0, it could be 5, it could be whatever. Unlike maybe like your arithmetic and geometric notations with the subscript. So to find the first term, we do make sure you look at that lower index, and it is indeed 1. So we're going to take the 1, plug it into the left. Now, n, we're only looking at the first term. So if the lower index is 1, and we're only looking at the first term, then the upper index is also going to be that same value. So we started at 1, we're going to have n equal 1 and plugged it on the right-hand side. And we have 2 over 1 times 2, which is 2. I was thinking of the answer, excuse me, 2 over 2. I'm not sure if I said that incorrectly or not. And we have 2 times 1 is 2. Over 1 plus 1 is also 2. And yes, we're done with step 1. 1 does equal 1. Now for space purposes, I'm going to go over here to the right and write our second step out, which is step 2. We're going to assume that S sub k is true. And that is, again, just rewrite your original problem, but take out the n's and replace them with k's. So we have the summation, as I starts at 1 and goes to now k instead of n, is, of 2 over I times I plus 1 equals 2 times k over k plus 1. Step 3. Write out the S sub k plus 1 statement. That's going to be the summation as I starts at 1. We're going to go to the k plus 1 term. 2 over I times I plus 1. Don't put your k plus 1 there, term there because there were no n's or k's there to begin with. We're going to go to the right-hand side and go 2 times k plus 1 over k plus 1 plus 1, which is 2 times k plus 1 over k plus 2. Let me double check that, make sure I got it right. Good. Now this should be what I get at the end of my proof if I've done it correctly. So, step 4, we're going to rewrite the S of k statement. So, right there. Summation as I equals 1 and goes to k of 2 over I times I plus 1. I'm going to leave some space so I can add that k plus 1 term to both sides. Okay, now, I know what the end of my proof should look like by the fact that I forced in the k plus 1 into our original equation. Now I'm going to go to this. This is my last, if I take the k and I plug it into this expression, I would get my s sub k term, my last term in the sequence. I want to take and add the s sub k plus 1 to both sides. So I'm going to take it and go 2. I'm going to take the I out, replace it with k plus 1. Take the I out, replace it with k plus 1, which is k plus 2. And then, you know where that came from, right? 1 plus 1 is 2. And that is the s sub k plus 1 term, and I'm going to add that to both sides. And now for the rest of my proof, I'm going to focus on just the right side of this equation until I get, hopefully, this right side that I had up here when I figured out what the s sub k plus 1 equation looked like, or the term should look like. Now I'm also going to rewrite the summation notation one more time because the upper limit was k, but I allowed it to go to the k plus 1 term. So I need to change my upper limit to the k plus 1. So I have the summation as I starts at 1 and goes to k plus 1, reflecting the fact that I extended the sequence by one more term. But we don't write the last term in summation notation, we write the expression. So 2 over I times, plus 2 over I times I plus 1 equals, now you might go, well, where did that go? I'm allowing it to absorb into this expression because we don't write a sequence of terms on the left side or behind a summation notation, but we do have the k plus 1 reflected still on the right-hand side. Okay, now to add these we need common denominators. This has a k plus 1 and this has k plus 1 and k plus 2, so we're going to multiply top and bottom of this first fraction by k plus 2. And we're then going to have to take this 2k and distribute it through those parentheses groups. We're going to have to clean up the numerator, refactor it, and then cancel, and again hopefully have that as our answer. So we have 2k times k is 2k squared. 2k times 2 is 4k. And then, because we have the common denominator now, I'm just going to make one big fraction, plus 2, over k plus 1, k plus 2. And I'm leaving the denominator in factored form because we only have one factor in the denominator, so some kind of cancellation is going to happen. All of these terms on top have a factor of 2, so we're going to pull that out. So we have k squared plus 2k plus 1 in our denominator. Now, what factors of 1 add up to be 2? 1 and 1, and we don't have any other choice anyway, because there are no other factors of 1. So this becomes 2 times k plus 1 times k plus 1 again over k plus 1 and k plus 2. Factor out the common factors, and voila, we get 2k plus 1 over k plus 2. That's what I should have gotten. So, bam! I am done. Go do your homework.